Okay, let's continue with Module 8 on interval estimation of a population mean, but we'll be taking up what we call the sigma unknown case now. First, let's just go back to our previous formula that we did in the first part of this module, x bar plus or minus z sigma over the square root of n. We called that the sigma known case because we're assuming we know the population standard deviation sigma. Many times this is simply not the case. If a researcher goes out to gather some data, they might have no idea of what the population standard deviation is. So we have to take up what we'll call the sigma unknown case. The logical thing, of course, to do is that since you're taking a sample, you could just use S, the sample standard deviation from your sample, to estimate sigma. And that's exactly what we're going to do. Instead of sigma here, we're going to put in S, the sample standard deviation. However, there's a slight problem with that. We've introduced another source of error in a way. We would like sigma over the square root of n in that formula, but we're using S over the square root of n. The biggest problem would be if S underestimates sigma. Then our margin of error actually would be too small. In a sense, we're going to correct for this by, instead of using the z distribution, we're going to use something called the t distribution. So we will use a t value rather than a z value in the formula. And our new formula is as on the right-hand side here, x bar plus or minus t alpha over 2 s over the square root of n. First, we have to learn some things about a t distribution. Unlike z, which was a single normal distribution with a mean of 0 and a standard deviation of 1, you actually have a set of t distributions. You actually have an infinite number of them. In general, they are symmetrical like z, and they have a mean of 0 like z, but the variance of each t distribution differs from other t distributions. T distributions are identified by a funny-sounding parameter called the degrees of freedom. Degrees of freedom are usually related to the sample size, and every time we get to a formula that uses the t distribution, we will have to tell you what the degrees of freedom are. In the particular case of this formula right here that we are now using, this is going to be a t distribution that has n minus 1 degrees of freedom. Now you really don't need to know exactly what degrees of freedom are. It gets into some mathematics that we don't need to go into. But they affect the shapes of various distributions in statistics, like the t distribution. And we'll see some other distributions later that also are identified by degrees of freedom. So I'm going to explain a little bit about degrees of freedom. But again, this will only go so far, but hopefully it'll help a little bit of understanding of degrees of freedom. We've said that the t distribution that we're using right now has n minus 1 degrees of freedom. You've seen the term n1 minus 1 before, back in Module 3 when we calculated a sample variance, s squared. We divided by n minus 1 rather than n. One of the reasons for that is that s squared is said to be a statistic that has n minus 1 degrees of freedom. What I mean by that is as follows. Remember, the summation of x minus x bar, without the square on it, the sum of the deviations around the mean, has to be 0. That means you could pick the first n minus 1 deviations around the mean to be anything you like, but the last one would have to be such that forces the deviations to add up to 0. That is, you've got a restriction here where you lose a degree of freedom. Let me give you a different example that might be simpler. If I told you pick 5 numbers, and you can pick them any way you want, you have 5 degrees of freedom. But if I said to you, pick 5 numbers, however the 5 numbers have to add up to 100, you have lost 1 degree of freedom. You only have 4 degrees of freedom. You could pick the first 4 numbers to be anything you want. But if the first 4 numbers, say, add up to 90, the 5th number would have to be 10 to force the sum to be 100. You were not free to pick that last number. Well, similarly, in the formula here for s squared, you can pick the first n minus 1 deviations to be whatever you want. That is the first n minus 1 values of x, actually. but the last one will be determined for you. Fortunately, as I said before, we really don't have to understand the theory behind degrees of freedom. We just need to know how many degrees of freedom there are in any given statistic we use. And as I've already told you, the first formula we're getting here with the t-distribution has n-1 degrees of freedom. If you want to read some more about degrees of freedom and kind of a cute little website to go to, I've given you a web address here that you can take a look at. Now we have to learn how to read a table of t-distribution values. Here I've put in a partial t-table. Now the t-table is going to be quite a bit different than the z-table because remember there was only one z-distribution, but there's an infinite number of t-distributions. So I can't possibly give you a table for every t-distribution. So what we're going to do is we're just going to give you a few selected t-values for any given number of degrees of freedom up to a limit. And we'll only be able to look at certain probabilities. So notice it's across the top it says area and upper tail. These are going to be the only probabilities that you can look up on the t-distribution. Is there a 20% probability in the upper tail, 10%, 5%, etc. Down the left-hand column we have the degrees of freedom. I've only put in a portion of the table here for 20, 21, 22, 23, or 24 degrees of freedom. In the middle of the table, these are the t-values. Notice that this is just the opposite of the z standard normal table, where the middle of the table has probabilities, and the z-values were across the top and down the side. The t-values you need are out in the middle of the table. So let's do an example. Suppose our sample size was 25, which would give us 24 degrees of freedom in the particular formula we're looking at now, and we wanted to get the correct t-values for 95% confidence. So we have 1 minus alpha is 0.95, alpha is therefore 0.05, and alpha over 2 would be 0.025. So we need to find the two t-values that leave 0.95 in the middle and 0.025 in each end. So we would go to the column in the t-table labeled 0.025, area and upper tail is 0.025, go down to 24 degrees of freedom, n-1, and you will find the t-value here to be 2.064. And remember the t-distribution is symmetric, so the positive and negative of that t-value will be the t-values that leave 95% in the middle and 2.5% in each end. So for a t-distribution with 24 degrees of freedom, and I often abbreviate degrees of freedom here as df, t-values of plus or minus 2.064 would be useful to us for a 95% confidence interval, and therefore leaving 5% in each, half of 5% in each end of the distribution for a total of alpha of 5%. Couple other notes about the t-distribution. If the sample size is less than 30, remember technically we should assume we're sampling from a normal population because the central limit theorem might not apply. However, a lot of research has been done that found that the t-distribution still gives us pretty good results for small sample sizes, even if that restriction is not satisfied. One of the reasons why a lot of textbooks use small sample sizes with the t-distribution is largely because of space limitations. Some books only give you the first 30 degrees of freedom, others go up to 100 degrees of freedom. But as I said, the t-distribution gives us pretty good results even with small sample sizes. One of the things that you can do with computers these days is you can have a computer randomly generate a population of numbers and then have it take samples of different size and apply the formulas that we're giving you, that is, calculate the mean and standard deviation, and see how good your interval estimates would be. And as I said, the t-distribution gives fairly good results. Let's do a problem. A manufacturing firm is trying out a new assembly line procedure in an attempt to improve output. 36 employees were assigned to try the new method. Assume the sample mean production rate for the 36 employees was 100 parts per hour, and the sample standard deviation was 15 parts per hour. Provide a 90% confidence interval for the population mean production rate. So notice here we have another problem where all of the statistics have been given to us for the most part. N is 36. We took a sample of 36. The sample mean was 100, and the sample standard deviation S is 15. And we want a 90% level of confidence. So our correct formula is going to be the x bar plus or minus TS over the square root of N, because sigma is unknown in this problem. X bar was given to you as 100, S was 15. 90% confidence if you go to your T distribution with 35 degrees of freedom. Remember that N was 36. You should get a T distribution value for 90% confidence of 1.690. Plug everything into the formula now. 100 plus or minus 1.690 times 15 over the square root of 100 will give you a confidence interval from 97.465 to 102.535. Our interpretation with 90% confidence, we estimate the population mean production rate is somewhere between 97.465 parts per hour and 102.535 parts per hour. By the way, let me back up for just a moment. One important thing about this problem is notice that the only thing in this problem that tells you to use the t-distribution formula rather than the formula with z in it is that you do not have the population standard deviation. You only have the sample standard deviation. So you have to look at the problem carefully and ask, do I know sigma or do I only know S? Here's a graph showing you how to find the t-values for this problem, in case you were confused on that. We have 35 degrees of freedom, so you'll go to the t-table with 35 degrees of freedom. We wanted a 90% level of confidence, so that's the area in the middle of the distribution. That means that alpha over 2 is 5% in each end of the distribution. So you would go to the t-table with 35 degrees of freedom, look in the column that says 0.05 area and upper tail, and you should get a z-value of 1.690. And then by symmetry, the other side is negative 1.690. Let's do one more problem that's going to be a little bit different than the ones we've done before. A quality control technician is checking the weights of a product. She takes a random sample of 8 units and weighs each unit. The observed weights in ounces are shown below. So here's the sample of 8 measured weights. Now notice in this problem, we didn't tell you what the sample mean is. We didn't tell you what the sample standard deviation is. We just gave you the data that was collected by a researcher. And you're going to have to take that data and calculate the sample mean and sample standard deviation. In addition, you're going to have to get the correct t-value from your t-table. So we want a 95% confidence interval for the population mean weight of the units. Technically, I'm going to assume that the population is normally distributed because we have such a small sample size. Now, using a calculator, or you can do this by hand, but if you remember from earlier in the course how to find a sample mean and sample standard deviation, the sample mean turns out to just be 51. The sample standard deviation is 3.07. We had a sample size of 8, so n minus 1 degrees of freedom is 7 degrees of freedom. Go to your t-table with 7 degrees of freedom. Go to the 0.025 column because the area in the upper tail will be 0.025 for 95% confidence. You should get a t-value of 2.365. Plug everything into our formula. 51 plus or minus 2.365 times 3.07 over the square root of 8. When you work it all out, you'll get a final confidence interval from 48.43 to 53.57. Our interpretation then, With 95% confidence, we estimate the population mean weight of this product is somewhere between 48.43 ounces and 53.57 ounces. And once again, what if you want to do this on a TI 83 or 84 calculator? Well, you can do that. Press the Stat button, scroll over to Tests. This time scroll down, probably onto the next screen, till you get to number 8 that says T interval, and choose it. Again, you have a choice between data and stats. Now, in the problem that we just did, where we gave you what I call the raw data, and you had to calculate the mean and standard deviation yourself, you would choose data. If you choose data, you have to go put your data in a list like L1 or L2, and then tell the calculator to go find that data. If you're using stats, like on one of the earlier problems we did, where you already know the sample mean and sample standard deviation were given to you, you simply press stats and then enter your sample mean, your sample standard deviation, your sample size, and confidence level. So for those of you with a TI 83 or 84, I would recommend going back to this problem and plugging in the data and using your calculator to get the confidence interval that you want for practice. Remember again here, if you have the raw data, you'll have to put this data in a list. And then, as I said a minute ago, choose data if you're entering your own data, and then go tell it to access the list that you want. That's the end of part 2. So far we've been estimating means. It's time to move on to estimating proportions.